Welcome to Lab 5. For this lab we headed down to the gym. We wanted to investigate the effect of the frictional force when it acts in the direction of motion and how it results in a change in kinetic and thermal energy. To do so, we employed the fundamental principles, the energy principle and Newton's second law. We set a block of ice on a treadmill and allowed it to accelerate as the belt of the treadmill generated a frictional force on the block of ice. We observed an increase in thermal and kinetic energy of the block of the ice and found that some of the ice melts in the process. But more on the results later. First, let's look at the physics. For this lab, we set the block of ice to be the system. Thus, through Newton's second law, we can say that if there are changes in the velocity of the system, there must be a net force acting on the block. We know that the frictional force is the only unopposed force that acts, so if we get specific measurements of these velocity changes, we can calculate the frictional force. Rearranging Newton's second law, we get the derivative of momentum equals F net, or the frictional force, simplifying our calculation. After calculating the frictional force, we can use the energy principle. Using the point particle model, we know that the change in energy of the system is equal to the work done on the point particle, which is equal solely to the change in translational kinetic energy. R1 here is the distance the block has gone relative to the ground. But now let's use the energy principle to describe the real change in energy. Here the change in distance, R2, is the distance the belt goes relative to the ground. This is easy to calculate since we can set the treadmill at a constant speed and easily calculate the distance it has gone during some time interval. Plugging that distance into the energy principle for the real work, we get the sum of the change in translational kinetic and thermal energy. Since we have already solved for the translational kinetic energy with the point particle model, we can easily find the change in thermal energy. Finally, we can find the amount of ice that is melted using our thermodynamic principles. Instead of our normal equation, which relates heat transfer to a change in temperature, we can use a similar equation with heat and amount of ice melted. This equation works on the basis that all energy put into the system goes into breaking bonds between the water solid, not raising the temperature. And HF refers to the heat of fusion, a constant for the material ice. To use this equation, we must assume that the ice is at 0 degrees and all heat generated is transferred completely into the ice. This is not unreasonable since the ice is just starting to melt when I used it. Now we are ready to collect data. We set the treadmill at 10 miles per hour or 4.47 meters per second. We measure the mass to be about 15 grams. We then set the block of ice on the treadmill and record. Importing our video into Tracker, we can generate position versus time data of the block by setting it on an arbitrary coordinate axis in the frame. Using Newton's second law, we can use the first few data points to calculate the frictional force by calculating change in position, then change in velocity, then change in momentum over time. Using this force along with the initial mass, position, and velocity of the block, along with the track speed and heat of fusion of the ice, we can initialize a Python code that will model several aspects of the physics on the block. The code may look complicated, but it really boils down to a while loop that just iterates through the physics we talked about before over a small time interval. Here's where we use Newton's second law. Here's where we use Newton's second law to calculate the change in velocity and position. Here's where the energy principle re-updates the translational kinetic, thermal, and total energy and outputs how much ice melts. Let's give the code a run. The block accelerates over the 1 second time interval as predicted in the direction of F net. Looking at the model in Excel, we see that the model in red is fairly accurate in predicting position, especially at the beginning. Since the model is initiated with some data from the beginning, it makes sense that it would be most accurate there. A discrepancy arises towards the middle and end, where the model overpredicts position. This could be because the block tumbles and turns a little bit, transferring some energy to rotational kinetic energy. Looking at the energy graph, we see the total or real system energy in blue, the thermal energy in red, and the translational kinetic energy, or the total energy predicted by the point particle, in green. The total energy increases at a constant rate because constant force is applied. The thermal energy is plateauing because theoretically, as the block reaches the speed of the track, less and less thermal energy is transferred into the system. In addition, the kinetic energy grows at an increasing rate because it goes up by the square of velocity. Finally, we can look at the total amount of ice that melts over time, which, since it is proportional to the amount of thermal energy, also increases at a decreasing rate. During the 1 second the block is on the track, which is going at 10 miles per hour, about 1/4 of a gram of ice is melted. The block accelerates to 1.6 meters per second. About 0.1 joules of energy are transferred into the system, 4/5 of those being accounted by thermal energy, and 1/5 of those being accounted by kinetic energy. All in all, this lab was a success. We modeled the frictional force and the changes in energy it created and used it to calculate how much ice melted. Thanks for watching.